what we're going to do today to start off with is I'm going to talk about the next part of our overview of Java threads. And in this discussion, we'll look at the implementation of the GCD Concurrent app, and you'll get a chance to see how the code works. Once we've done that, we'll also discuss the pros and cons of the various Java thread programming models that we've been discussing up to this point, so you can see what the comparisons and trade-offs are. First, just give a quick overview of the runtime behavior of the GCD Concurrent app. This app uses threads to compute the greatest common divisor, or the GCD, of two numbers, which is defined as the largest positive integer that divides two integers without a remainder. And you probably already know what a GCD is, but in case you forgot, you can take a look at this link. So I launched the program. As you can see, it gives me a couple of different ways to run the code. And one approach is going to run the GCD program using a Runnable. That's this one. So if I click run Runnable, it'll go ahead. And what it's doing is it's computing GCD for some God knows large number of iterations, millions and millions of iterations. And every so often it's printing a result, because otherwise we'd have the screen just absolutely chock full of results. We don't want to do that. So you can see over here it says it's entering run with a thread ID of whatever, and then it's running, and it's computing GCD for various things. So that's the approach that uses a Runnable, and we'll look at that code next time. Then we also have another approach that uses a thread that we've subclassed from, and again, it's just printing the results. For both those examples, we're just running one thread at a time. So we have one thread that runs that uses the Runnable approach, Runnable programming model for creating some code for a thread. The other approach, we have the subclassing a thread model of getting things to run, that programming model. And then this one, run thread Runnable, will go ahead and actually spawn two threads, one of which is doing it with the Runnable, one of which is doing it by subclassing thread. And then those are running in the background. And you can see there's lots more output because they're both running concurrently. And that's producing the results that we're seeing here. So what we'll do next time is I'll walk through the code, which you can take a look at online. It's all part of the examples that are part of the course. But I'll go through the examples in detail. And we'll take a look at how the threads are created. And then we'll also talk about some of the deficiencies with this particular implementation. And this particular implementation doesn't really try to do anything very sensible under certain circumstances. And let me see if I can show them to you. So let's go ahead and run this stuff. And while it's running, let's go ahead and rotate the screen. And you can see what happened. When I rotated the screen, all of a sudden it just stopped running. Let's try that again so you can see it better. So here we go. We're running. We rotate the screen, and it stops. It doesn't keep going. And so you'll see that the first implementation that we do here, when it's rotated, just shuts everything down. And we'll talk about later, we'll talk about why that's a problem. And we'll talk about various mechanisms that are provided in Android in order to ensure that when a rotation takes place, things are still able to keep running. And we'll talk about a bunch of different ways to do that. We'll talk about saving and restoring state. We'll talk about using these get last retained instance techniques, and then we'll talk about how to use retained fragments. So there's a bunch of different ways in Android that you can keep your program running even when the screen orientation changes. And if you take a look at the programming assignment that you have, actually I think all of them, they all have this implemented already. It's implemented in the gazing simulation activity class. And I think that they all use the retained instance technique, which is really, really easy to do. We'll look at some other more sophisticated techniques later that can be used in other circumstances. But one of the cool things is if you run your program and you rotate the screen, or if you run the test program which rotates the screen, you'll see that it continues to run even when you rotate it. And that is kind of the goal you should aspire to, because it's really annoying if you're watching a video on YouTube or your YouTube app and you rotate the screen, wouldn't it be annoying if it stopped and you had to go back and start from the beginning? That would be really annoying. The YouTube app doesn't work that way. When you rotate it, it keeps track of where you were, and it keeps running the video after you've rotated it. And you want your programs to do that too. So we'll be talking about that as we get a little bit more into the mechanisms that Android provides. So what I'd like to do now is just give a quick overview of the design of the app, and then we'll look at the code. So here's a UML class diagram that illustrates the key classes. There's a few other ones, but these are the key ones. You can find the code at this link. The lifecycle logging activity class is a class I use a lot in my examples because it's real helpful for debugging your code. What it does is it overrides many of the lifecycle hook methods that are defined on an activity and logs the fact that that method was called, that hook method was called, to the Android logcat output. And that way you can see at a glance kind of what your program's doing. So when you look at the program and watch it run, you can see that this logging pops up. Just gives you a sense of what's going on. Main activity then extends lifecycle logging activity, which in turn extends activity. And the main activity, as the name suggests, provides the main entry point into this app. And its primary purpose for this particular app is to handle the button presses from the user. So when the user presses the buttons to run the different versions of the application, then those things go ahead and are handled by the main activity. Depending on which button you push, you'll get different behavior. You'll get the same behavior with different structure. One approach is going to use the so-called GCD Runnable class, which computes the GCD of two numbers by implementing the Runnable interface. So that's one approach that's used. The other approach that's used is to use the GCD thread class. And what that does is it computes the GCD of two numbers by extending the thread superclass. So those are basically the different ways that things work. And now we're in the source code for the app. So you can see here we've got a couple of things. We've got a manifest file, and the manifest file basically just says, here's the activity that's going to be called when this particular app is launched. This is the main activity. And you can see here that that's going to call the main activity, which is nestled down in the main activity folder. And this says that when this app is started, this is the main activity that starts. So let's go ahead and take a look at the activities. There's a couple of different folders here. We have utils, which do a few helper class method-like things like pop, toast, and so on. Probably won't spend a lot of time talking about that unless you're curious. Here, the main thing we're going to focus on, these are the activities. Here's lifecycle logging activity. As you can see here, all this does is it simply logs the output for each of the hook methods that's called back. So when onStart is called, it logs that onStart's called. When onResume is called, it logs that onResume is called, and so on. It also calls up to the superclass to make sure that the superclass method runs. But this is basically just a way to log things. Where does it log to? It logs to logcat. So if you were to run this, you would take a look at the Android monitor, and that would be where the output would be. I think that was probably covered by Mike when he was here. So let's go over to main activity. Main activity is, as the name suggests, the entry point into the app. You can see that main activity extends lifecycle logging activity. It defines a couple of fields that are used to display the output, as well as to be able to contain the results of the text view. The text view is nested inside of a scroll view so that the output scrolls so you can see it if it goes longer than what's on the screen. Pretty obvious thing to do. Here's the onCreate hook method, as hopefully you recall from earlier coverage of Android that you may have had, or if you've gone back and watched the earlier videos. The onCreate method is the hook method that's called when an activity is first launched. This is called automatically by the underlying Android Activity Manager service. Yes, Ann? We don't have an onCreate and lifecycle logging activity. I don't think we do, because that's a slightly different purpose. It's really meant for the various hook methods that are used to control the lifecycle. So this is the one that we have here. Oh, I take it back. There is one. There is indeed a call to onCreate because it checks to see what the bundled state was. So yes, there's a call to onCreate. Oh, okay. So the question is, you can see here, we're overriding. onCreate is overriding the superclasses onCreate. Let's go look at the onCreate method. Here is the superclass onCreate method. So you can see that here's the lifecycle logging activity, which extends activity. Here's onCreate. When onCreate is called, it follows this pattern where it calls up to its superclass first, and then it goes ahead and it logs the activity that's happening. It logs what's happening. It says onCreate's being called. Main activity, as you can see here, overrides onCreate, and the very first thing it does is it calls up to its superclass, which in this case is lifecycle logging activity. So that ensures that the superclass's onCreate method is always called back. And this is a very common pattern you see used in a lot of frameworks such as Android to make sure that everything gets called properly. Okay, so once the onCreate method is called from the parent, we then set the content view, and that basically describes how the screen will be laid out. I won't go through that at the moment, but you can take a look at the XML file and see how it's laid out. That's the main activity layout file, which is over in the resources layouts directory. And then we go ahead and we call the find view by ID method to get ourselves cached or stored instances of the two UI controls that are being exposed. So we have the text view log, which is where the text goes, and that, as I mentioned before, is nestled inside of a scroll view. So this is just setting up the user interface. This user interface isn't anything particularly fancy. It's just used to be able to display the output. And if you go back and watch the video that shows how the program runs, you'll see how it works. All right, so that's kind of setting things up. That's, the onCreate method is only called one time when the program starts. Now, when the user actually clicks a button, they click the Runnable or the Run with Thread or whatever they click on the UI, then the way that Android works is it'll go ahead and dispatch these methods. And these methods are actually set over here. Let's go ahead and take a look in the resource directory, in layout. Here's main activity. And we actually want to look at this as text. Oh, by the way, these are the buttons I was just talking about. Run, Runnable, Run, Thread, and so on. Let's go take a look at the actual text for this. So this is the layout. And the main thing I want to point you to is the onClick attribute. So for this button, this is the one that's the Run Runnable button. Here's the Run Thread button. Here's the Run Thread and Runnable button. These different buttons each have an onClick handler defined. Run Runnable, Run Thread, and Runnable. Those correspond to these methods here. So that's how Android glues together the methods that are exposed to the application and the UI to the actual implementation of those methods. So when you click on Run Runnable, this is the method that gets called back. And you can see what it does is it goes ahead and it creates a new GCD Runnable, passing in this activity. And because this is the Runnable version, it goes ahead and creates the Runnable, and then it creates a thread passing that Runnable in as the parameter to the thread. And once it does that, it goes ahead and starts the thread. So that's the Runnable implementation. Here is the thread implementation. You can see this is a little different just to make it fun. What we do here is we make ourselves a new thread, and then we use the so-called fluent interface pattern, or idiom. I guess it's really a pattern because it can be used in multiple languages. And what we do there is we make a new thread, new GCD thread, open close paren, dot set activity. That works off of the object that was returned from new GCD thread, which makes a constructed object, passing in this. So we're setting the activity to this activity. And then it takes the result of that, which is again a GCD thread, or thread, and it calls set random, and it makes a new random number. So that's what's called a fluent interface style. And you see that used it's all the rage these days in almost every programming language that people use. Okay, so, and then we go ahead and start the thread. So that's another way of doing things. The third way is just to show something fun, just to give you yet another way to do stuff. This is the Run, Thread, and Runnable. And if you go back and watch the video of the app, you'll see that when you click this button, it goes ahead and starts multiple threads that run concurrently. And what we do here to do this is we make ourselves a new array list of threads. And then we go ahead and we add a new thread using the fluent interface style for GCD thread. So we add a new thread to the list. Then we go ahead and make another thread, which this time we have a new GCD Runnable. That uses the Runnable way of doing things. So now we have two threads. And then we say for each thread in the thread list, call the start method. This is what's called a method reference. This is basically saying call start on each of the thread objects. That will cause the threads to start. And then down here, we go ahead and we spawn another thread. And this thread is going to go ahead and wait for those other threads to finish. And I'll explain why we do that in just a second. But for the moment, bear with me that what we're doing here is we're going to create a new thread. This is giving it a lambda. And that lambda is saying, wait for each of these threads to finish, and do that by calling join on them. And after everything's done, we go ahead and print an output that says all the threads have been joined in a particular thread. And notice down here, just because we're using lambda expressions and anonymous objects just to show off all the cool things you can do in Java 8, we're saying new thread. We're making an anonymous thread with a lambda expression, and then we're calling start on it. So this will go ahead and start a new thread that will then wait for the results of these other two threads. Yeah. And
that thread to just synchronize everything?
Great question. So that was where I was headed. What's the reason why we have to spawn a thread to do this? You know, obviously, syntactically speaking, we could write this code without spawning a thread. We could just, right after thread list.forEach, thread start, we could say thread list.forEach, and then we could do this join lambda. Why do we spawn a thread? Yes, Hamid. Exactly. So the issue here is if we don't spawn a separate thread, then the user interface thread will wait for those other threads to finish. And those threads, depending on what values they have and how long it runs, they could block for a while, because it might take many seconds to compute all the GCDs, depending on various factors like how fast is your processor and how many cores do you have and so on. So we don't want to have the user interface thread blocked during that time. Does anybody know what happens if the user interface thread blocks for any period of time on Android? What'll happen?
The whole application is shut down.
Well, it could be shut down. Yes. Paul? You get an exception or a dialog called application not responding, or an ANR. And so ANRs are an indication that something's taking too long to run in the user interface thread, and then you're given a chance to terminate. So it doesn't shut it down right away, but it's considered a bad design flaw if you got an ANR. Yes, Duncan.
So how does this sort of prevent the UI thread from blocking? It just sort of replaces it?
Oh, great question. So what'll happen here is you'll have, let's say you have two threads off running GCD. There's the UI thread, which is what's calling back to this particular method when you click the button. And by spawning another thread, now we have a third thread, or actually it's a fourth thread at this point, because we got two threads, the UI thread. Now we have let's call it a waiter thread. And the only purpose of the waiter thread is to sit off to the side waiting for the other two threads to finish. Control at this point will return to the UI thread, and it can sit there and do other things. For example, and we'll see this later with later examples, you could have it set up to cancel. So you could cancel if you said, these guys are off and running. I don't want them to run anymore. I'm going to cancel. You could click cancel, and the UI thread would be responsive to that.
So that's just an automatic thing. You don't have to, if you spawn a thread that waits, it sort of just knows to give control back to the UI.
Yeah, good question. So the question is, and this is nothing, there's nothing Android-centric in my answer here. When we create a separate thread, and this thread starts to run, that basically it forks, that's not quite the right word, but it launches or spawns another thread. And the control just continues. So whatever happens to occur after this start method is called will continue to run. In this case, that method returns, and it goes back to the Android event loop. So that's just a general characteristic of threads. As a rule, is when you start them, then they run concurrently with other stuff. And if the calling thread, the one that launched the waiter thread in this case, and the other two threads for that matter, that thread will keep doing whatever it does. In this case, it returns back to the UI. But yeah, those are really good questions. Any questions about that? So this is a not very complicated example, but it shows you a whole bunch of things about core concurrency concepts and how things can run concurrently. Here's the actual, this is a kind of a fun method. This is called printline, and it's kind of a ripoff of the Java printline stuff, but it doesn't work quite like that. Here's what it does. This method, you'll see when we take a look, this method gets called at various places whenever we want to display something to the display, we want to write to the text output. You can see here, for example, text view log.append. That's taking the string to print and putting it in the text view. And then we're scrolling down the scroll, so it goes to the next line. So here's what we do. This is really neat. This is a fun idiom. I use this a lot in my Android programming. So what we do is we make ourselves a command, which is a runnable, and we initialize that runnable with a lambda. And so this is just a piece of code that will get stored in this variable, this local variable, and then can be used later. And then we go down here and we do something really clever. Remember that you can only write to the user interface, you can only write to the display from the user interface thread. So you can't write to the user interface thread from a background thread, right? So what we're going to do here is the following thing. We're going to check to see if we're running on the user interface thread or not. And if we are running on the user interface thread, in other words, if we were called from the user interface thread, and there's a couple of calls up there that illustrate this, then we're just going to go ahead and run this command, right? We made ourselves a runnable, and we just say run, because we're in the UI thread. We're done, right? But if we're called from a background thread, if we're called from a thread that's not the user interface thread, we call the run on UI thread method. The run on UI thread is an activity method. It's defined in the activity class. And what it does is it takes a runnable and it puts it onto an internal queue that's part of the Hammer framework, Hammer standing for handlers, messages, and runnables. It puts the command, in this case it's a runnable, it puts the runnable onto a queue, and then it lets the main UI thread pull that runnable off, and then it'll go ahead and run the command, and as you can see what the command does is it goes ahead and appends things. So we're either going to run the command on the UI thread if we're already there, or we're going to queue up the command to be run on the UI thread later. And later in this case is almost instantaneous. But the point is that we're getting it to run on the UI thread. So that's a super cool little idiom that you can use. And that way you don't have to know or care where you're calling your operations from, the UI thread or the non-UI thread. You can just say print line, give it something to print, and it'll figure out on its own how to print it properly. Any questions about that? It's a clever little idiom. In fact, let's take a quick look and see how that idiom is implemented over here. Here's UI utils. And if you take a look, we have running on UI thread. And what this does is it says, is the calling thread, thread.current thread, is the calling thread the same as the looper's main thread? If the answer is yes, we're running on the UI thread. If the answer is no, false, then we're not. And this, we'll talk about this later. There's something in Android called the looper. And the looper is something that keeps track of threads. And there's a main looper, which is the UI thread. Yes?
So back there, instead of doing the check, why can't you just do run UI thread?
Oh, yeah, good question. Yeah, very good question, in fact. Let's take a look. So we could have just said run on UI thread. Just because, and run on UI thread basically does that check. I just wanted to show this idiom, just to illustrate how you could do it. We could just call run on UI thread, and it would do a check internally. It's almost the same thing. The final thing we'll show is the OnDestroy method. OnDestroy is a hook method that automatically gets called back by the Android Activity Manager service, which is kind of the traffic cop of all things that are activity and service and broadcast receiver related stuff. All the components are used to dispatch that. And that gets called back when the activity is going to be destroyed. There's a couple of cases where activities get destroyed that matter. One is when you click the back button. So you're running in your app, you click the back button, that takes you out of the app. That'll cause OnDestroy to be called. And the second place that it gets called is if you rotate your phone. So if you rotate your phone, that will shut down the current activity by causing onPause, onStop, OnDestroy to be called. And then a new activity will be created. And when you rotate the phone, going from, say, portrait to landscape mode or landscape mode to portrait mode, whichever one, that will cause the current activity to be shut down and a new one to be created. Does anybody know why Android does that? What's the reason of destroying and recreating activities when rotation occurs? Exactly. So layout change. Oftentimes you'll have, various multimedia objects, multimedia components like media players or figures or images or whatever, and you want them to look different if they're in portrait mode than landscape mode, because they'll you'll rescale them. If you're in portrait mode, which is taller than it is wide, you want to use a figure like this. If you're in landscape mode, where you're wider than you're all tall, you might want a figure that looks like that. So the way Android works is when you do the rotation, it'll go and grab the right kind of image depending on what mode you're in. Yeah?
Why wouldn't you distinguish and have like an on rotate rather than like both be on destroy?
Well, there's ways of figuring out in OnDestroy whether you're being destroyed because of a rotation or not. There's a method called something like is changing configuration. We'll see it later. I don't remember off the top of my head, but something like that. Is configuration change or whatever. And what that basically means is destroy is being called, but it's because of a rotation. So you can actually flag that case. So they didn't actually have a separate method for OnDestroy. They just have a way to tell why you're being destroyed. And why you're being destroyed may differ how you react to being destroyed. Now, the key thing to note here is that something is missing here, right? And we're going to cover this in a later example once we've talked more about interrupts and so on. So we're not actually handling rotations properly or destruction properly in this code. In particular, the thread is still running in the background, right? Even though it's now going to be disconnected from the activity. So we'll fix that later. I just want to point that out at this point. OK, so that's the activity. Let's now go take a look at the various implementations. Here is GCD Runnable. As you can see, this extends random and implements Runnable. We'll talk more about that later. We keep track of the activity that's used to create us. We keep track of a couple of fields that are really constants that keep track of how many iterations and how many print iterations. So you can see by default we have, I think it's 100 million iterations, and every 10 million or so we will print something. So 1/10 of the time we print. Here's the constructor. You can see it just takes the activity and stashes it away. Here's compute GCD. This is the guy that actually does the GCD computation. And you can see here it's a very simple recursive call that checks for the base case, which is the number equals 0. Otherwise, it calls itself recursively modding number 1 by number 2. So you can look up the algorithm for GCD to convince yourself that's correct. I was just doing something simple. It's really just a way to burn up CPU time. Down here is the run hook method. That's what's going to be called back, as we discussed the other day, when the thread starts that this runnable is a part of. As you can see here, we take a string that's going to be used to print a little prefix that indicates the thread ID and so on. Then we go ahead and print entering run with the thread string. And now we go into a big loop. And this loop loops for the max iterations. And every time through, it calls next int. Next int is a method inherited from random that produces a random number. And then we go ahead and every 10 million iterations, we're going to print out the current GCD. So that's just to avoid spewing out too much print on your screen. So you can see here, every 10 million iterations, we're going to print out the GCD of number 1 and number 2 is the GCD computation. And that'll run for a while. And when we're done, we go ahead and print we're leaving the run method. This is just to show you something to do. It's not really intended to be profound programming. But the key thing I want to point out here is this is a runnable. And because it's a runnable, we can extend some other class. Like we can extend random, as we show in this case. And we can implement runnable. Let's go take a look at GCD thread. So GCD thread uses the different programming model for threads. In this case, we extend thread. We make ourselves have a field that's a random number generator object, have the same iterations and print iterations. And notice that in this case, we don't have a separate constructor. We have a set of setters that are used for fluent interface style. And this is the way you program fluent interfaces. We have a method called setActivity here. And that is used to set the activity. And then it returns this object, returns a GCD thread. And then we can compose that by calling setRandom. So after we make ourselves a new GCD thread object, we can say new GCD thread, open close paren, dot setActivity, this, dot setRandom, and then we'll give it a random number generator, which gets stored in a field. And then we return this. So this allows you to chain those calls together. That's what's called a fluent interface. So that's just to show how it works. I could have made a constructor that did that. I just wanted to show fluent interfaces. GCD numbers, the compute GCD is the same. This is basically the same. The only difference between this and the other one is that we use the mRandom field to generate the random number. Okay, so that's basically the implementation of that application. Any questions about that? So I'll give you a real quick answer, but to really understand this, it's kind of part of the prerequisites, so go back and watch some videos from the earlier material that you have access to. So in Android, there are 4 main types of architectural components in the Android model. There are activities, which are really for defining user-facing operations, like getting button presses from a user or displaying output and so on. There's services, which are components that run in the background and do long-running tasks or tasks that access network resources, for example. There are broadcast receivers, which are used to handle events that are generated, which are sort of intended to be kind of asynchronous. And there's something called content providers. And content providers provide structured storage to be able to access data, things like your list of emails or a list of instant messages or whatnot. Activities, being user-facing, are the thing that you're used to actually present the screens to the user and to be able to interact with the user. So that's what an activity is. It interacts with the user. And you can learn all about that in the other videos. Okay, what I'd like to do now that we've taken a look at the source code, I want to go back and discuss the pros and cons of the Java thread programming models that we've been looking at. And we'll take a look at them from a couple different points of view. First, let's talk about pros of extending thread. So if you take a look at the GCD thread example, that extends thread. And this is very straightforward, right? You just extend one class and you override the run method and you fill in other methods or fields that you need to do in order to get the job done. So that's very simple. So you can see here we define ourselves with these setters like set activity, we have an activity field, and so on. The other nice thing about extending thread is it consolidates all the state, in other words, all the fields, and all the methods in one object. So fields and state, they're all nicely pulled together. And this can be useful if you have to manipulate the thread state during runtime configuration changes. Now, the example we just looked at didn't illustrate this, but we'll see this later. And so by having everything in one place, both the thread and the behavior, it only requires you manipulating one thing. So that makes it more convenient in some ways. And we'll talk about this in a couple of upcoming lessons on managing the Java lifecycle and managing multi-threaded activity state. You'll get a chance to see examples where interrupting or restarting threads is easier if we have their state connected to the thread object itself. There are some downsides, however, with extending thread. And one of the downsides, of course, is that a subclass, in this case GCD thread, must extend the thread superclass. Well, why is that a downside? It's a downside because it's restrictive, since Java only allows one subclass per superclass. And if we extend thread, we've just used up our one superclass. Now we can't have our GCD thread extend anything else, because you only get one per Java class. Well, a subclass can only extend one superclass. And that's just a Java-ism. There's a variety of reasons for it. I won't go into in detail unless you're curious, but basically it prevents certain headaches about the dreaded diamond of death and ambiguous state and so on. So one of the pros, therefore, of implementing a runnable is that a subclass can implement multiple interfaces. So unlike extension, where you can only have one superclass, you can implement multiple interfaces. And so we don't actually do this, but we could. We could implement Runnable, which we do. We could implement serializable, which we don't, but we could. So you could have many things that you implement, and that allows us to be able to then have another way to extend something. So just for fun, we could implement many interfaces, but still extend something else. We could extend random, just to give it something else to do. So that way we can have multiple things that we implement and then only extend one, but we haven't burned up our one superclass by extending thread. Runnables are also very flexible because we can use them in different contexts. So we won't talk about this right away. We'll talk about this later when we get to the lesson on Java Executive Framework. But one of the consequences of using the runnable-based approach is we can actually create ourselves a runnable, just like we did before, except rather than directly making a new thread and giving this runnable as a parameter to the thread's constructor, instead we could use the Java thread pool executor. We could have a fixed thread pool or a variable size thread pool or whatnot, and we'll talk more about those later. And then we could go ahead and reuse that same runnable and execute it in a different context. So we could now have multiple threads that would run, and we'll see some examples later that do this. We could have multiple threads that would run these runnables. So runnables give us this opportunity to be able to run them in a different context, whereas threads are kind of bound. When you extend from a thread, you're kind of bound to using it with that thread and starting that thread, whereas runnables give you more flexibility. So that's one of the benefits of using runnables. The downside or con of using Runnable, however, is that there are more moving parts involved. In particular, you've got runnables and you've got threads or executor services or whatever, but you've got these things are split now. We've got multiple things. And this can get more complicated if a program needs to be able to access the state of a runnable, but it only holds a reference to the thread object. So remember before, if you extend thread, then your instance of your subclass both has ways to get to the state of your subclass as well as be able to do thread things to it, like interrupt it. When you split, so if they're centralized, they can be used together. When you split them apart and have a runnable and a thread or an executor, now you've got to keep track of more things if you want to be able to access the state and also manipulate this object as a thread. So that gets a bit more complicated, right? So you have to sort of decide what it is you're trying to do and which is the right approach. In practice, most Java and Android software typically implements Runnable rather than extending thread. There are many exceptions to what I just said, but that's a common practice. And we'll see examples of both throughout the class. And of course, Lambda expressions are now becoming very popular on Java 8 platforms. And Lambda expressions are basically anonymous runnables. So they fit under the runnable thread model. All right, so that's the end of this whole lesson. We're now done with the overview of Java threads.